Question 57 is difficult for two reasons. First, you'll have to make a judgment call based on vague standards. It demonstrates when using shortcuts won't get you close enough to the values needed. Second, the solution given by the NCEES is confusing, complicated, and contains errors. Initial critical thought solution elements. 1. What are you solving for? The steady-state energy flow required to heat mixed air to a desired temperature. 2. What is the fundamental process? Moist air mixing and determining a sensible heat load. 3. What are the first considerations to find the solution in connection to the fundamental process? Knowing the properties of standard moist air and how they affect heat transfer rates. 4. Are there key assumptions? Adiabatic mixing, sea level conditions, and steady flow. This video is brought to you by ExOverZero, which offers the best PE study tools possible. To purchase our practice exams, use the link below. From the question, it's obvious that you need to solve two problems. First, an air mixing problem, and second, an energy flow problem. Beginning with the air mixing problem. When it comes to fluids mixing, whether they're air, liquid, or steam, mass always matters. All authoritative sources for HVAC calculations say that mixing conditions are determined by using mass, enthalpy, or humidity ratio. All three are directly connected to pounds of mass. There's a relatively common rule of thumb equation that can approximate conditions for mixing air, which uses CFM instead of mass. The advice given for using CFM to calculate mixed air temperatures is that the two streams which are mixing must not be too different in their temperatures. How different can they be and still work? There's no objective standard. The further apart the two temperatures are, the further off the result of the calculation will be. This is because density of air is different at different temperatures. Radically different temperatures means radically different masses. Using CFM is a judgment call based on vague standards, and there's no golden rule cutoff point for temperature or density differences. The best practice standard for calculating mixed air conditions is to use mass, enthalpy, or humidity ratio, and never to use CFM. Take note, in question 45 of the NCEES practice test, CFM is used in the provided solution. They opt to show you that approximation is close enough in that case. Then again, they were the ones who wrote the question and the possible answers, so they knew beforehand that approximation would be okay. If you use mass, and not CFM, to solve question 45, you'll still get the correct answer. The danger in using CFM is that you may be too far off, but using mass will always get it right. The delta T of mixing air streams is 40 degrees in question 45. The delta T of mixing air streams is 88 degrees in question 57. For question 45, they're close enough to use CFM. For question 57, they're not. Accuracy should win in the decision between rule of thumb approximations and proper calculation techniques. Don't get caught having to choose between the two options, because you'll be asking yourself, how far off is too far off? And thinking through these decisions wastes time. Having to check your answer against the possible answers in the multiple choice wastes time. Using CFM doesn't save you time in this testing circumstance, so don't use it. Now, to solve the air mixing problem for question 57. According to ASHRAE Fundamentals Chapter 1, Equation 44, the state point of the resulting mixture lies on the straight line connecting the state points of the two streams being mixed, and divides the line into two segments, in the same ratio as the masses of dry air in the two streams. Put another way, the mixed air temperature is a straight, linear proportion based on the masses of the input streams. Set up the equation like this. The mixed air temperature is equal to the low temperature airstream plus the ratio of high temperature airstream mass to total mass times the delta of airstream temperatures. On a hypothetical psychrometric chart, it can be demonstrated like this. Here is the low temperature airstream, given as negative 20 degrees. Here is the high temperature airstream, given as 68 degrees. The mixed air temperature will be somewhere in here, the delta of the airstream temperatures. You'll find it based on the ratio of masses of the two airstreams. To find the masses of the two airstreams, you must connect the size of the airstreams to the weight of the airstreams. You're given the size in cubic feet per minute. You'll need a unit of pounds per cubic feet to determine the weight of the airstream. Pounds per cubic feet is density. Specific volume is the reciprocal of density. Look up the specific volume of the two entering airstreams in the NCEES Mechanical Reference Handbook in Section 7.4. Note: use the dry air masses. The NCEES solution uses the moist air at saturation masses. This is incorrect. Look at ASHRAE Fundamentals, Chapter 1, Equation 44 for proof of this. At negative 20 degrees, the specific volume of dry air is 11.073. At 68 degrees, the specific volume of dry air is 13.299. Take the reciprocals and multiply them by the volumetric flow to get mass flow. 1,000 CFM times 0.09031 equals 90.310. 3,000 CFM times 0.07519 equals 225.581. Total mass flow of the combined airstreams is the sum of these, 315.891. Applying this to the mixed air temperature equation, negative 20 degrees plus 225.581 divided by 315.891 times 68 minus negative 20 is equal to 42.84 degrees. The mass ratio of the 68-degree airstream is 0.714 of this line. So the mixed air temperature will be 71.4% up this line here. The mixed airstream is now 4,000 CFM at 42.84 degrees. This must be heated up to 75 degrees. Because the temperatures are dry bulb, use the sensible heat equation to determine the BTU per hour needed to do the job. This is found in the NCEES Mechanical Reference Handbook, Section 9.1.7. It's shown in this general form. For standard air at sea level, it can be simplified to this. Again, the solution provided by the NCEES is problematic. It uses this. Where does this come from? It's a reconstructed version of the sensible heat equation. It substitutes this total mass flow for these, the flow rate and the density. It then assumes a humidity ratio of 0, meaning this zeroes out. Somewhat complicated. But ask yourself, is the mixed air standard air at sea level, It sure seems to be. Even the NCEES admits it's standard if you look back at our old friend question 45. All the temperature ranges and flows in 45 encompass the temperature range and flow of the mixed air in question 57. And they use the simplified standard sensible heat equation. No substituting variables or reconstruction based on assumptions that the humidity ratio is 0. It just uses this straightforward standard equation. So do the same and make life simple for yourself. 1.10 times 4,000 CFM times 75 degrees minus 42.84 degrees equals 141,504 BTU per hour. The nearest option in the multiple choice is D, which is the correct answer. The NCEES solution gives 145,855 BTU per hour. This is a variance of 4,351 BTU per hour, or 3%, which can be attributed to choosing saturated moist air density rather than dry air density, and assuming 0 humidity ratio rather than the standard of 0.01, as given by ASHRAE Fundamentals Chapter 18, Equations 8 and 9. To get good at questions like this, read ASHRAE Fundamentals Chapter 1, Section 10, Subtitle Adiabatic Mixing of Two Moist Airstreams, Example 4, and Fundamentals Chapter 18, Equations 7 through 10. Also, do ExOverZero problems 45 and 57 in tests 1 through 4.